Now going to chapter 2, analyzing the results of network reconnaissance. The foundation topics are threat management, point-in-time data analysis, packet analysis, protocol analysis, traffic analysis. As you can see on the first page, I have point-in-time data analysis, data correlation analysis, and analytics, data outputs, and tools. So we're going to start with one of the foundation topics, point-in-time data analysis. Point-in-time analysis captures data over a specific period of time and thus provides a snapshot of the situation at that point in time or across the specified time period. The types of analysis described in the section involve capturing the information and then analyzing it. Although these types of analysis all require different tools and processes, they all follow this paradigm. Packet analysis. Packet analysis examines an entire packet, including the payload. Its subset protocol analysis, described next, is concerned only with the information in the header of the packet. In many cases, payload analysis is done when issues cannot be resolved by observing the header. While the header is only concerned with the information used to get the packet from its source to its destination, the payload is the actual data being communicated. When performance issues are occurring and there is no sign of issues in the header, looking into the payload may reveal error messages related to the application in use that do not present in the header. From a security standpoint, examining the payload can reveal data that is unencrypted that should be encrypted. Also can reveal sensitive information that should not be leaving the network. Finally, some attacks can be recognized by examining the application commands and requests within the payload. Protocol analysis. As you just learned, protocol analysis is a subset of a packet analysis, and it involves examining information in the header of a packet. Protocol analyzers examine these headers for information such as the protocol in use and details involving the communication process, such as source and destination IP address and source and destination MAC addresses. From a security standpoint, these headers can also be used to determine whether the communication rules of the protocol are being followed. Traffic analysis. Whereas protocol analysis looks at the information contained in the headers and packet analysis looks at the content of the payload, traffic analysis is concerned with the types of traffic in the network because this information is contained in the headers. Traffic analysis is done with protocol analyzers or with NetFlow analysis, which is covered in the next section. In many cases, you're interested in the traffic statistics rather than individual communications themselves. When traffic analysis is used for performance issues, the following items might be of interest: network utilization, download or upload speeds, type and size of packets. However, malicious individuals may be interested in analyzing traffic patterns to discover any existing vulnerabilities. The following are some of the clues that they might look for. Stations having conversations of how long and when the sizes of packets. Stations having conversations for how long and when. The sizes of packets, which can indicate the type of communication. For example, large packets for file transfer versus very small ones for interactive sessions. Information about TCP/IP, TTL, window size, dot fragment, bit, and type of service TOS, which can be used to identify the operating system. Next topic, NetFlow Analysis. NetFlow is a technology developed by Cisco that is supported by all major vendors and can be used to collect and subsequently export IP traffic accounting information. The traffic information is exported and using UDP packets to a NetFlow analyzer, which can organize the information in useful ways. It exports records of individual one-way transmission called flows. When NetFlow is configured on a router interface, all packets that are part of the same flow share the same following characteristics. 1. Source MAC address. 2. Destination MAC address. 3. IP source address. 4. IP destination address. 5. Source port. 6. Destination port. 7. Layer 3 protocol type. 8. Class of service. 9. Router or switch interface. When the flow information is received by the analyzer, it is organized and can then be used to identify the following: the top protocols in use, the top talkers in the network, traffic pattern throughout the day. Next topic. Wireless analysis. Wireless analysis involves capturing 802.11 packets. While it serves the same purpose as wired analysis, the approach to the analysis is somewhat different, given the fact that there are many more frame types in the wireless LAN environment due to all the additional management traffic required to maintain order in the wireless LAN, or WLAN. An understanding of the contention method used in wireless LAN, CSMA-CA, which is quite different from CSMA-CD, is required as well. CSMA-CA. In 802.11 wireless networks, CSMA-CD cannot be used as an arbitration method because, unlike when using bounded media, the devices cannot detect a collision. The method used in called carrier sense multiple access with collision avoidance, CSMA-CA, it is much more laborious process than carrier sense multiple access collision detection, CSMA-CD, because each station must acknowledge each frame that is transmitted. A typical wireless network contains an access point and one or more wireless stations. In this type of network, called an infrastructure mode wireless network, traffic never traverses directly between stations but is always relayed through the access point, or AP. The steps in CSMA-CA are as follows: carrier sense multiple access, collision avoidance, CSMA-CA. Step 1. Station A has a frame to send to Station B. It checks for traffic in two ways. First, it performs carrier sense, which means it listens to see whether any radio waves are being received on its transmitter. Then after the transmission is sent, it continues to monitor the network for possible collisions. Step 2. If traffic is being transmitted, Station A decrements an internal countdown mechanism called a random backoff algorithm. This counter will have started counting down after the last time this station was allowed to transmit. All stations count down their own individual timers. When a station's timer expires, it is allowed to send. Step 3. If Station A performs carrier sense, there's no traffic, and its timer hits 0, it sends the frame. Step 4. The frame goes to the AP or access point. Step 5. The AP sends an acknowledgement back to Station A until Station A receives the acknowledgement. All other stations must remain silent. For each frame, the access point needs to relay. It must wait its turn to send using the same mechanism as the station. Step 6. When its turn comes up in the cache queue, the frame from station A is relayed to station B. Step 7. Station B sends an acknowledgement back to the access point. Until the access point receives the acknowledgement, all other stations must remain silent. As you can see, the process creates a lot of overhead, but it is required to prevent collisions in a wireless network. There are also a set of attacks and vulnerabilities in a wireless LAN that are not found in a wired network. A person performing analysis must understand and be able to recognize these attacks, which include the following: war driving, war chalking, rogue access point, WLAN sniffing. War driving is a process of riding around with a wireless device connected to a high-power antenna, searching for wireless LANs. It could be for the purpose of obtaining free internet access, or it could be to identify any open networks that are vulnerable to attack. While hiding the SSID may deter anyone who knows how to use wireless sniffer could figure out the SSID in 2 minutes, so there really is no way to stop war driving. War chalking. War chalking is a practice that used to typically accompany war driving. Once a war driver located a WLAN, she would indicate in chalk on the sidewalk or on the building the SSID and the types of security used on the network. This activity has gone mostly online now, and there are many sites dedicated to compiling the list of found wireless LANs and their locations. Just as there is no way to prevent war driving, there is no way to stop war chalking either. Rogue access points. Rogue access points are the APs that you do not control and manage. There are two types of APs, those that are connected to wire infrastructure and those that are not. The ones that are not connected to the wire network present a danger to your wire and wireless network. They may have been placed there by your own users without your knowledge, or they may have been purposely put there by a hacker to gain access to the wire network. In either case, they allow access to your wired network. Wireless Intrusion Prevention System WIPS devices are usually used to locate rogue access points and alert administrators of their presence. WLAN sniffing. Just as a wire network can be sniffed, so can a WLAN. Unfortunately, there is no way to detect this when it is occurring, and there is no way to stop it. Therefore, any traffic that is sensitive should be encrypted to prevent disclosure. Data correlation and analysis. When raw data is generated, it can be in various forms. It can be subjected to a number of different types of analysis. The following sections look at available types of analysis and scenarios in which they're applicable. Later in the chapter, you will see some examples of output generated by various security devices and scanning tools. Anomaly analysis. Anomaly analysis, when applied to any of the scanning types discussed in this chapter, focuses on identifying something that is unusual or abnormal. Depending on the type of scan or on the information present in the captured traffic, this could be any of the following. Traffic captured at times when there usually is little or no traffic. Traffic of a protocol type not normally found in the network. Unusually high levels of traffic to or from a system. As you will learn in the upcoming section on IDS or intrusion detection systems, many IDS and IPS intrusion prevention systems are anomaly based, which means they identify malicious activity by identifying unusual network behavior. One of the main disadvantages of this type of detection is the large number of false positives typically generated by these systems. While a false positive, which occurs when unusual traffic is identified as a threat, but it is not a threat, are not as dangerous as false negatives, which occur when malicious traffic is not identified as a threat. False positives can over time cause technicians to become complacent. Trend analysis. Trend analysis focuses on the long-term direction in the increase or decrease in a particular type of traffic or in a particular behavior in the network. Some examples include the following: an increase in the use of a SQL server indicating the need to increase resources on the server, a cessation in traffic bound for a server providing legacy services, indicating a need to decommission the server, an increase in password resets, indicating a need to revise the password policy. Many vulnerability scanning tools include a pre-configured filter for scan results that both organizes vulnerabilities found by severity and charts the trend up or down for each severity level. Availability analysis. As you might expect from the same, availability analysis focuses on the up and down status of various devices in the network. Typically stated as a percentage of uptime, it is often used as a benchmark in service level agreements. For example, 99% uptime for a year would indicate that the device in question must be down for no more than 8 hours, 45 minutes, and 57 seconds over the entire year. In some cases, however, other factors besides raw uptime are used. Some reliability monitoring tools also look at throughput, up-down status or status of individual components, and possibly maintenance issues. For example, if it is said that a particular component has 95% maintenance for 1 hour, this means that there is a 95% probability that the component will be repaired within an hour. Heuristic analysis. Heuristic analysis determines the susceptibility of a system to a particular threat risk using decision rules or weighing methods. It is often utilized by antivirus software to identify threats that cannot be discovered with signature analysis because the threat is either too new to have been analyzed, called a zero-day threat, or it is multi-pronged attack that is constructed in such a way that existing signatures do not identify the threat. Behavioral analysis. Behavioral analysis is another term for anomaly analysis. It also observes network behaviors for anomalies. It can be implemented using combinations of the scanning types already covered, including NetFlow, protocol, and packet analysis, to create a baseline and subsequently report departures from the traffic metrics found in the baseline. One of the newer advances in this field is the development of user entry behavior analytics, UEBA, User Entity Behavior Analytics. This type of analysis focuses on user activities, combining behavior analysis with machine learning. UEBA enhances the ability to determine which particular users are behaving oddly. An example would be a hacker who has stolen credentials of a user and is identified by the system because he is not performing the same activities that the user would perform. Data output. A security analyst needs to be familiar with the types of data generated by the scanning and analysis tools described in the first part of this chapter. The following sections look at examples of various output and make some general comments about reading the information. The aim here is not to learn the details of any specific vendors, product, but rather to gain a general idea of what you're looking at and you're looking for. Firewall logs. Firewall logs can vary widely in appearance, but generally list each interaction of the firewall with the respective traffic traversing it. In its simplest form, a firewall log is a text file showing each of these interactions. As an example, in the figure that you see in front of you, it shows the Windows firewall log. As you can see, it shows the type of information included in a firewall logs, including the following: source and destination IP address, source and destination MAC address, source and destination port number, and action taken. The next figure shows an example of using a firewall log to detect an attack. This firewall log has been filtered to show only traffic destined for the server 192.132.209.179. Some of the traffic is normal, but look at the info column in the display at the far right. It indicates that all the packets have Syn flag set. If we saw traffic from this device, we would see it answering every packet with a Syn ACK packet. Very interesting. So it's a Syn Flood Attack. This is a classic case of a Syn Flood Attack, but this one is not a regular one. These packets are all coming from different source IP addresses, which is probably how they all got through the firewall. That means that this is a distributed denial of service attack coming from many devices. Moreover, because most of the source addresses are private, they're coming from inside your network, which means that the problem could be a peer-to-peer botnet in which one of the local devices has the command and control software installed on it. Interesting. Now, if we look at the next image, it's a Windows firewall log viewer. Yes. Oops. Sorry, guys. I'm just moving over. So, do we have 2.6? Yes, we might have 2.6, but I think I went for further 2.6. Yes. Okay, so it is a classic case of a Syn Flood Attack, but this is not a regular one. These packets are all coming from different source IP addresses, which I already said, right? So, moving on, packet captures. Let's see if I can get that image for packet captures. Windows firewall, yes. Packet capture tools can vary in how they look, but they all contain the same general information about each packet capture because all TCP/IP packets have the same structure. The tools allows you to see all of 4 layers of the TCP/IP model present in the packet. When packet capture is focused on an individual packet in a set of capture packets, the tools will show all 4 parts: the link layer with the source and destination MAC address, the network layer with the source and destination IP address, the transport layer with the source and destination port numbers, and the payload or data. So if you see at the let's take a look at the typical screenshot. This is a TCP SYM packet. So frame, this is the physical layer and describes how many bytes were on the wire. Ethernet 2, this is the data link layer and contains source and destination MAC address. So remember, guys, the data link layer contains the source and destination MAC address. Internet Protocol version 4, this is the network layer and contains the source and destination IP address. So the link layer contains the source and destination MAC address, and the network layer contains the source and destination IP address. Transmission control protocol, this is a transport layer and contains the source and destination port numbers. Don't forget that. TCP is a transport layer and contains the source and destination port number. Data of some type. This is the raw data. There's no data in this packet because it is a SYN packet, part of the TCP handshake. But if this were HTTP data, for example, the section would be titled HTTP data and would include the raw data. Okay, so if we look at figure, okay, HTTP post 7, an HTTP packet has been highlighted, and the layer 4 section transport layer has been expanded to show the source and destination ports. Then below there are the 7 flags with an indication of which are on and which are off. Which ones are on and which one are off. On and off. In this case, the ACK and the PSH flag are set, or push flag. And at the very bottom, the data portion is highlighted, revealing the data content in the lower right corner. Because this packet is unencrypted, you can read this as an HTTP post command along with its details. Nice. So we can see that. Let's see if we have another one. Okay, unencrypted HTTP password. In packet analysis, the emphasis is on what is in the data portion. As in 2.8, the section with the data is highlighted and the details pane displays its content. In this display, the data HTTP, and because the data is HTTP and because the data is unencrypted, you can see the password on the highlighted part of the details. Oh, there you go. That's the password. Okay, cool. Of course, you know we're using Wireshark for all this as a tool. Right? Okay, so Nmap scan results. So let's see if I have a screenshot of an Nmap scan. Yes, I do. Okay, ping scanning involves identifying the live host on a network or in a domain namespace. Nmap and other scanning tools such as ScanLine and SuperScan can be used for this. Such a tool records responses to pings sent to every address in the network. It can also be combined with a port scan by using the proper arguments to the command. To execute this type of scan from Nmap, the command is, as you can see, Nmap dash lowercase s capital P and the IP address. So this is 192.168.0.0.0 to or through 100, where 0 through 100 is the range of IP addresses to be scanned in the 192.168.0.0 network. So in the figure, it shows an example of the output. All devices that are on are listed. For each one, the MAC address is also listed. Okay, so you can see the example there. You know, it started 192.168.0.1 MAC address. Okay, and Nmap scan report 192.1. So the ones that are on, it's giving you the list. Just as operating systems have well-known vulnerabilities, so do common services. By determining the services that are running on a system, an attacker also discovers potential vulnerabilities of the service and may attempt to take advantage of them. This is typically done with a port scan in which all open or listening ports are identified. Once again, the lion's share of these issues would have been mitigated with proper security patches, but it is not uncommon for security analysts to find that systems that are running vulnerable services are missing the relevant security patches. Consequently, when performing service discovery, patches should be checked on systems found to have open ports. It is also advisable to close any ports not required for the system to do its job. Nmap is one of the most popular port scanning tools used today. After performing scans with certain flags set in the scanned packets, security analysts and hackers can make certain assumptions based on the responses received. These flags are used to control the TCP connection process and so are present only in those packets. So let's see if we have another. Yes. So figure 210 shows a TCP header with the important flags circled. Normally flags are turned on as a result of the normal TCP process, but a hacker can craft packets to check the flags he wants to check, I guess. Security analysts and hackers alike can perform scans with these flags set in the scan packets to get responses that allow them to make certain assumptions. Event logs. Every device includes some sort of event log that contains various messages concerning the activities that have been processed by the machine. Some contain a single log that contains all message types, while other devices have multiple logs, each of which focuses on different types of events. For example, a Windows 10 computer has the following logs: application, security, setup, system. Let's see if I have a screenshot of that. Yeah, Windows security log. Oh, look at that. Okay. In other cases, such as with a router, there's a single log for all events. Technicians use various commands to extract the exact information for which they're looking for. Syslog. Syslog is a protocol that can be used to collect logs from devices and store them in a central location, called a syslog server. A syslog provides a simple framework for log entry generation, storage, and transfer that any OS, security software, or application could use if designed to do so. Many log sources either use syslog as their native logging format or offer features that allow their logging formats to be converted to syslog format. Each syslog message has only 3 parts. The first part specifies the facility and severity as numeric values. The second part of the message contains a timestamp of the host name or IP address of the source of the log. The third part is the actual log message with content as shown here. Sec number, I believe, timestamp, percentage, facility, severity. What I'll do is I can probably show you a screenshot of that and see if I can just, oops, excuse me. So let's see. So what exactly this is talking about? Here you go. See, so the same. So in the following sample, syslog message generated by a Cisco router, no sequence number is present. It must be enabled. The timestamp shows 47 seconds. Since the log wasn't clear, the facility is link, an interface, the severity is 3, the type of event is up and down, and the description is interface gigabit changed to state up. So I'll show you both samples here of what they're saying. And right now they're talking about the Cisco, which is the one below, right here. Up and down, and the description is being changed state up. Okay, this is good. So this sample is a locally generated message on the router and not one sent to a syslog server. When a message is sent to the syslog server, it also includes the IP address of the device sending the message to the syslog server. So I might have a sample of that also as well. And yes, syslog server, look at that. So we do have one. Okay, no standard fields are defined within the message content. It is intended to be human readable and not easily machine parsable. This provides very high flexibility for log generators, which can place whatever information they deem important within the content field, but it makes automated analysis of the log data very challenging. A single source may use many different formats for its log message content, so an analysis program needs to be familiar with each format and should be able to extract the meaning of the data from the fields of each format. This problem becomes much more challenging when log messages are generated by many sources. It might not be feasible to understand the meaning of all log messages, and analysis might be limited to keyword and pattern searches. Some organizations design their Syslog infrastructure so that similar types of messages are grouped together or assigned similar codes, which can make log analysis automation easier to perform. As log security has become a greater concern, several implementations of Syslog have been created that place a greater emphasis on security. Most have been based on an IETF RFC 3195, which was designed specifically to improve the security of Syslog. Implementations based on the standard can support log confidentiality, integrity, and availability through several features, including reliable log delivery, transmission confidentiality protection, and transmission integrity protection and authentication. IDS report. An intrusion detection system also creates a log of every event that occurs. And let's see if I have also a figure for that. Yes. The figure that you see before you shows output from an IDS, which it's blurred, but right now it's only theory we're going through. In the output, you can see that for each intrusion attempt, the source and destination IP address and port numbers are shown, along with a description of the type of intrusion. In this case, all the alerts have been generated by the same source IP address. Because this is a private IP address, it is coming from inside your network. It could be a malicious individual, or it could be a compromised host under the control of external forces. As a cybersecurity analyst, you should either block the IP address or investigate to find out who has the IP address. Make sense? Now there's another one. Let's see if I can. It's a bit better, I guess. While the logs are helpful, one of the real values of an IDS is its ability to represent the data it collects in meaningful ways it reports. So on the figure that you have in front of you, the 215 shows a pie chart created to show the intrusion attempts and the IP address from which the intrusion were sourced. Okay. Tools. This chapter has already taken a look at some of the types of output that can be generated by various devices. The following sections, we examine some of the tools that generate this output, as well as a tool that pulls all this output together for easier analysis. SIEM, S-I-E-M. Security Information and Event Management. For large enterprises, the amount of log data that needs to be analyzed can be quite large. For that reason, many organizations implement a Security Information and Event Management, SIEM, S-I-E-M, which provides an automated solution for analyzing events and deciding where the attention needs to be given. Most SIEM products support two ways of collecting logs from log generators. Agentless. For this type of collection, the SIEM server receives data from the individual host without needing to have any special software installed, and those hosts, some servers, pull logs from the host, which is usually done by having the server authenticate to each host and retrieve its logs regularly. In other cases, the host pushes the logs to the server. And let's see if I have any. Oh yeah, there you go. Security Information and Event Management System. Okay. Usually involves each host authenticating to the server and transferring its logs regularly, regardless of whether the logs are pushed or pulled. The server then performs event filtering and aggregation and log normalization and analysis on the collected logs. Agent-based. With this type of collection, an agent program is installed on the host to perform event filtering and aggregation and log normalization for a particular type of log. The host then transmits the normalized log data to a SIEM server, usually on a real-time or near real-time basis, for analysis and storage. Multiple agents may need to be installed if a host has multiple types of logs of interest. Some SIEM products also offer agents for generic formats, such as Syslog and SNMP. A generic agent is used primarily to get log data from a source for which a format-specific agent in an agentless method are not available. Some products also allow administrators to create custom agents to handle unsupported log sources. For the moment, I will go ahead and stop my recording so we can continue on part 2.